face of the group, huh?
Wow.
Oh,
Non-participating party.
You were asleep at like 7:30? I was golfing. At nighttime? I don't golf at night.
Give their methods and results him out.
No, that doesn't make sense.
But you knew that we were meeting up, didn't you? From the group chat?
So you just made plans? You took away from our time for your time. Just tell me your time's more important than the group's time.
I think you're a selfish, shellfish.
Did you find that it appears some students aren't understanding portions of the paper?
I'm not mad, I'm disappointed.
No,
I'm mad. We walked all the way to
I have a
support
number
Katie.
of.
It's something she was passionate about, and you didn't have the common decency to go support it.
You should not support
Yeah,
my
we're-
passion, Sam.
Yeah, mine are
You don't know how twisted this passion is.
What?
What is this passion?
All right.
I do Spotlight because I like to blind people.
All
For
right.
like theater.
Dr. Judd and I have your methods and results for the Henry summary. Ready to head back to you with our comments on them. Be sure and read the comments. As I was reading mine, there are a number of you who are struggling with understanding all of the aspects of the paper. There are also a number of writing issues, almost all of which are dealt with in your writing guide that was a part of the required books for this course. Also, if you have any questions about any of the comments, hopefully by now you're recognizing Dr. Judd's handwriting versus my handwriting. Come and talk to either of us about that. We both know how to write, luckily. Any questions over what we were doing last week? All right. So we were talking about these quantitative traits that have normal trait distributions and are underlain by multiple genes all contributing to the trait. And we talked about how you can measure heritability by just conducting a regression between the offspring phenotype and the parental phenotype. And we talked about what happens if you exert selection on this population as if you were doing artificial selection experiment. And what that does is it changes the average parental phenotype that is breeding, and as a result that brings about a change in what you would expect the average offspring phenotype to be. And so this is selection, this is the evolutionary response to selection, and heritability basically transmits the degree to which changes here get translated into changes here is by that slope. So in this particular example, the mean of the parental population changed 2.41 inches. You multiply that times what the heritability is, and you get the evolutionary response to selection. This is called the breeder's equation because it can be used to project how much evolutionary change is going to go on if you happen to be like a farmer and you're trying to breed, better milk production in your dairy cows or whatever. And so you see that the response in the offspring is less than the force of selection on the parents, but that's because heritability wasn't perfect. There wasn't a heritability of 1. When you're done with that, though, you have a reduced population that you're working with, and you'll see that now the slope is 0.665. One of the things that directional selection, and that's what this type of selection is, one of the things that directional selection does is it eats up genetic variation. So if we took this population and selected against it some more, against the short individuals in this case, we would move the population towards a taller average phenotype, but over time, the selection that we exert on this will have less and less of an effect because you're getting rid of all of the alleles that contribute to shortness, and you're only retaining those alleles that make individuals tall, until you finally get to the point where you have a population where everybody is the same height, And so you've totally exhausted the variation that there is for that trait. So this is seen in declining heritability over time. And so we can see that the heritability here is 0.9165, and the heritability here is 0.6615. Less variation in parents, less variation in offspring. And that's what heritability ultimately is. It's a measure of genetic variation. For years, I was curious as to why heritability is designated h squared, because this is heritability. So heritability is 0.9615 or whatever it was in the first case. But you don't square this or anything. It's just this is the symbol for heritability. And I finally found out that the guy who invented this technique was kind of a statistician as well as a biologist. And S squared is the symbol for variance. And because heritability is basically a measure of genetic variance, he used a similar kind of notation to identify genetic variance because it related back to kind of sample variance. And that's why it's h squared. But on a test or something, don't try and take the square root of it or something to get what h is. H squared is the symbol for heritability. So, Darwin's finches, the finches that you guys are studying, back in the 1970s, there was a drought. The drought killed off a bunch of medium ground finches, Geospiza fortis, the same species that your paper is about, that you're reading. As these were declining, you could tell that it was related to declines in seed abundance. If you're in a drought, the plants aren't reproducing, the plants aren't growing, so the plants aren't reproducing, so the plants aren't producing seeds. So as seed abundance goes down, so does the population of finches. But what was also happening during this time period is not only was the seed supply declining, but the characteristics of the seeds themselves shifted. And it isn't because all of a sudden plants, so they went from kind of soft seeds to hard seeds to kind of soft seeds again. And it isn't that plants are producing different sides of seeds, it's that there is a pool of seeds out there available. As the birds start eating them, they start eating the easy to access seeds first until those seeds decline, and then only the most difficult seeds, the big hard seeds, are left to eat. And then at the end of this thing, once again, they've eaten all the small seeds, they've eaten all the large seeds, and at this point, seed abundance begins to go up, presumably because the drought is abating, and you have more seeds available, so they go back to having small seeds available. During all of this, during this time period when all of the small seeds have been eaten and only large seeds are available, you see that there's an evolutionary shift in the size of the beak of the finch, from relatively small beaks to larger beaks, representing directional selection acting on beak morphology. This is long-term data, looking at that decline. Let's see, beak size. Looking at this body size, beak shape. Sorry, I was thinking one of these population size. Looking at this increase in beak size, so this is beak size, during the late 70s, but then after the drought was over, you can see that there's no longer any selection, and the beak size is going back to kind of normal. This is presumably what is happening in Academy Bay during the 2000s after 1970. You no longer have selection pushing some subset of the population towards either big beaks or small beaks. You actually have selection acting on the population in a more stabilizing way, leading to intermediate sized beaks. You've seen this figure before. This is essentially heritability. In 1976 in the red dots, and 1978 in the blue dots, one of the things that you will notice about the variation in the parental population in 76 is it spans this entire axis. What happens to variation in the parental population in 1978?
There's a less diversity.
There's less genetic variance because all of these small-beaked parents are not there. That shift is due to an evolutionary change such that the average parental phenotype in 78 is up here around 10. It was down here around 9.5 beforehand, and that leads to a difference in the offspring that are going to be produced from those two sets of parents. So once again, these heritability graphs, these parent-offspring regressions, relate back to the breeder's equation. The reason that we call this the breeder's equation is because it's actually used pretty often in agriculture. So this is a long-term experiment, 100 generations of growing corn. And in this population, they started off with about 5% corn oil content. So you can select for corn oil, either a lot of corn oil or very little corn oil. And what you see is that when you select for high oil content, the population responds. There is an evolutionary response to this artificial selection, and it gets higher and higher and higher and higher. If you select, starting with the same population, select for low oil content goes down. But what's happening to oil content in this set of lines? It's decreasing, but is it decreasing at the same rate that the continuous high oil lines are increasing? No, it's not. It's decreasing at a decreasing rate. What's your explanation for why that's happening? In this case, they reversed. They took these lines and reversed and started selecting for low oil. And you see that they start responding immediately and strongly to that selection. But when we reversed here to produce more oil rather than less oil, they're responding, but they're responding much less slowly, or much less quickly. Why is this one set of lines responding so poorly to the selection that is being exerted?
Because they can't be replenished at the same rate.
What do you mean by replenished?
Like, in the homework, there's, like with population,
No, presumably these are growing just fine. They're just not responding to the evolutionary pressures of selection. As far as I know, the oil content of corn doesn't have any effect on its viability.
Yeah, really each generation here is about the same population size, about the same yield maybe.
Yeah. To get a response to selection, you need two things, right? You need heritability and you need selection. If you're exerting selection on the population and it's not changing very much, what must be happening?
it's not very heritable.
It's not a very heritable trait because you're basically selecting away all of the genetic variation. And so those low oil content lines have very little genetic variation simply because you're down here at the bottom. There's zero, whatever genes are leading to oil content in corn, you've lost all of the alleles that are adding oil content to the seed. So that when you reverse it, it does go up, but it goes up much more slowly than it goes up here, and it comes down much more slowly than it does here. The other thing you'll notice is that these two lines, they then reverse it again and start taking this high oil treatment and reversing it and selecting for high oil content, and they start to go, the black line starts to go up. But what's happening to the black and the yellow line? They're not the same slopes either. They're beginning to do what with one another out here at the end? Yeah, they're converging on one another because, of course, what's now happening at the high end of the oil content spectrum?
It's starting to average out.
Once again, be more specific. Yeah, once again, we're starting to lose genetic variation up here. So this population that has been undergoing selection for a long period of time, that selection has eroded the genetic variation, just like we saw in the Finches. This one was selecting for high oil, then selecting for low oil, and then back selecting for high oil. But the fact that they're now converging probably means that they're becoming more and more genetically similar to one another, and you're going to hit a plateau up here, probably between 20 and 25% oil content, when you've basically exhausted genetic variation at this end of the spectrum, just like these have exhausted genetic variation at the low end of the spectrum. So that's what selection does, directional selection does. It eats up genetic variation until you finally get a population where everybody's the same, because everybody has the same genotype for whatever genes are determining this trait. Questions about this? When we talk about selection, we've seen this before, haven't we?
Not in this class yet.
Not in this class, okay. We can also think about selection acting on human populations as well. This is a selection surface. It should look kind of familiar to you because it kind of looks like the horn lizard paper, where there was selection against one side of the distribution of the phenotype, and there was little to no selection once you reach this plateau where you have horn lizards that were bigger. This is actually birth data from human beings in Europe in the 1940s. And what you see is that if you're below a certain birth weight, if you're a preemie, your probability of surviving is really low. But also you see this little dip down at the end here, where also if you're too big, your survival probability goes down slightly. Now, survival is way lower if you're a preemie than if you're too big, but there is selection at both ends of this. This is largely directional, but there's also this pushback at the high end. Presumably that's because the female birth canal, the space that you have to pass a baby through, is ultimately constrained by the structure of the pelvis, the rigid skeletal structure of the pelvis. And if you get a baby that is too big, it physically won't fit through the pelvis, and that leads to complications. Now, we've gotten better at caring for preemies, and so preemie survival has gone up since 1951. What else have we done about selection at this end?
C-section.
C-sections. If the baby's too big, just cut it out of the belly, no problem. But as you do that, whatever selection was tying baby size to hip morphology is being broken up, because these babies survive now, so human height might be getting bigger and bigger because selection is now more directional than it was before, but there's no selection against females with small hips. And so we can disrupt these correlations between traits. The last case that we'll talk about traits that are correlated with one another. And these later slides, these slides, they're in here. We're not going to go through them because they're more applicable to the last case study. So from the snakes on, ignore the slides in this presentation that's on Moodle. We'll cover that when we talk about snakes and newts later in the semester. Questions about this way of thinking about genetics? If I give you a heritability and a selection strength, you should be able to predict what the response to selection is going to be using the breeder's equation. If I give you a parent-offspring regression, you should be able to use that parent-offspring regression and any information like an equation on that thing to tell me what the heritability is, et cetera, et cetera. Okay? Questions? Yeah?
Will we get like a practice assignment for doing that?
I have not prepared a practice assignment, but there's not a ton of practice because we haven't taught you how to do regression yet. So, like, really it's just a matter of reading an equation which is already in the slides. I'll think about one. We have one for the next set where we have to deal with multiple traits because that's a little more complicated. This is actually really uncomplicated. This is the slope of the line. I'll have to give you what selection is, and it's just a matter of working the equation. So I can make a practice assignment, but it would be pretty dull, actually. If you're still having difficulties with it, come by and see me. All right. And now Dr. Judd is up. for you guys, he did not have to stay for jury duty, and he didn't get stuck with me for density-dependent growth.
Did.
Why?
You sit there and judge people.
What's that? Who's being judgy?
Who had jury duty?
I did.
You didn't get to stay?
No, they let us out about a half hour ago.
I appreciate you coming back.
Yeah, I'm glad I could make it easy. Okay, so we're gonna talk about density-dependent population growth, and the reason that I'm excited to talk to you guys about this is because the density-independent growth was a portion of the exam that you all did reasonably well on. So we're gonna build on that. We're gonna add to it. So I want to take a moment and review this concept of little r, the parameter that we talked about last time. Then we're going to compare the density-independent growth model for populations with the density-dependent model that we're going to introduce to you. We'll talk about carrying capacity. We'll talk about intraspecific competition, so competition among individuals of the same species. We're going to talk about birth rate and death rate and how they go into R and how they relate to carrying capacity. And eventually you shall have some mastery over each of these parameters, right? Your population size, carrying capacity, and the per capita or instantaneous rate of increase. So that's the roadmap. So let's think once again about R. Now, I think last time we talked about this, I was referring to it as the instantaneous rate of increase. It's also commonly referred to as the per capita rate of increase, and I tried to use both. I'll probably be using per capita a little bit more in this lecture, and we'll talk about why we use some graphs. So what is R? It tells you it's a parameter that tells you the rate at which the population is growing for a given population size when you're dealing with an exponential model. You should remember that it's the natural log. We calculated it as the natural log of lambda, or the finite rate of increase. And you should remember that that was 1 plus r, and that r was b minus e, so you could kind of recombine it in this way. The reason I put this slide in, I added this slide from last year, is in the homework, I asked you about whether you thought natural selection could be occurring if a population is undergoing exponential growth. And really the key with natural selection, right, is differential fitness consequences for some trait. That's one of the important premises of natural selection. And if all individuals, all female individuals, or in the case of plants, all individuals, were reproducing to their fullest potential all the time, all the babies they could have, they were having, then the exponential growth would be determined by the maximum possible R value that that population could have. If that's the case, then there's no differential fitness consequences. Everyone's reproducing all the babies they can. But as long as the real R value, the actual R value of the population is somewhere between its maximum potential and 0, the population can grow exponentially, and natural selection can, in fact, occur even as the population grows. So they can grow exponentially as long as R is greater than 0, but R doesn't have to be the maximum for that to occur. So I just wanted to clarify that. Hopefully, if you look back at your notes on that homework, you'll see this will make a little more sense. What's important both with that discussion of R and with this density-dependent model we're going to talk about here is that trait variation can lead to differential survival and reproduction, right? So we've been talking about the finch beaks for now. Variation in the size of the beak can influence ability to acquire food, acquire seeds, right? Maybe access nutrients differently, especially when things get scarce. And so the ones that are better equipped for certain traits for accessing food resources like these seeds that the finches are accessing are going to be able to allocate more energy and resources to their reproduction and have higher fitness. So here was our equation, our model for exponential growth. Who can remind me in plain English what this dNdt term means? How could you describe dNdt in plain language? Yeah.
The change in population over the change in time.
Yeah. It's the rate at which the population is changing. Notice here we've got time on the x-axis and population size on the y-axis. dNdt is not one of the axes. We're just looking at, but what we are seeing is that because we're dealing with R, per capita rate of increase, larger the population gets over time, the steeper that tangent line is, the faster the population is increasing. Population increases faster and faster. And in fact, when you switch this around to put the rate of increase on the y-axis and the population size on the x-axis, you can see that as the population increases, the rate at which the population is growing also increases in that exponential model, in that unlimited resources type of model. And of course, the slope of this line is constant. That's going to be where R comes from. So, why did you all say that this model was unrealistic for tortoises on Pinta Island? Yeah.
Because there's not like an infinite amount of plants and food for them to eat.
Right. Eventually, there's going to be some resources that might be limiting, such that the population cannot increase indefinitely. And the simplest model that we're going to talk about today that incorporates that increase in scarcity of resources, that increase in competition, is a logistic model. So it's got this kind of stretched out S-curve to it. And it's bounded between 0, no individuals in the population, and some maximum that it approaches. So this is the model we get when the growth of a species feeds back negatively onto its own rate of increase. What does that look like? Well, here was our initial model. All we're going to do is add a new term to it, this parenthetical term. So once again, we've just talked about these parameters. Make sure you can identify each parameter or variable in the model so that you can read it in plain language. The rate of increase equals the per capita rate of increase times the number of individuals in the population. And in the logistic growth model, we're adding this. A new component that we're just multiplying by Rn to model the effect of individuals of a species affecting their own growth rate negatively. So we're going to talk about where this K comes from, how to think about it, and how to use it. Then remember how we rearranged this equation such that you could predict a population size at some point in the future, at some time in the future. Then remember what the corresponding equation for this looked like if you integrate it. I didn't give you the equations. I didn't really ask you to memorize them, but hopefully they're familiar. Yeah, give it a shot.
Is it the NT equals N0 ERT?
Yeah, or N0 N naught. That's that first, that starting. Yeah, good. N naught times e raised to the RT. We can also integrate this one, but the equation becomes quite large. So we're not going to ask you to integrate here, just as we didn't ask you to integrate here. But I want you to see that you can do it, right? And this K term shows up down here in the denominator, and we could predict the population size at some time, knowing the rate of increase, the time, the population size initially, and this K value. Does anyone know what K means from the prep homework? Keep track of who else. Anyone new? Remember?
Sustainable population size.
Yeah, the maximum sustainable population size, the carrying capacity. So K is going to represent our carrying capacity. Trevor, thank you.
Trevor, you're so slow. Not so brain addled that you can't catch a 10. Good.
So where does this K parameter come from? Where does this carrying capacity come from? Well, recall that growth in a population that's closed comes from two things, right? It comes from births and deaths. And we discounted immigration, emigration, individuals coming and going, because we're dealing with a closed population. Well, to get to K, let's think first about death rates and how they might change under a scenario of limiting resources. And then we'll think about birth rates and how they might change under scenario of limited resources. So here we've got in italics here the per capita death rate. So again, I'm calling it the per capita because we're dealing with exponential, not geometric growth. So this is births per unit time per population size, per individual. We've got the per capita death rate if there's no limitation, if there's no competition for resources, there's plenty of resources to have all the babies you can. And then we've got this new parameter C, the strength of density dependence, and N, of course, is still the number of individuals in the population. So who recognizes the form of this equation? What kind of a function does that look like? If you think of your, let's see, if we think of the death rate, the per capita death rate as kind of the y-axis, and the population size, N, as the x-axis, what kind of equation does that look like?
Linear?
Yeah, it's a linear equation. Good. And what's the slope of that equation going to be? Yeah, it's going to be C, some positive value here, C. Good. So that might make some intuitive sense that the larger the population size, the larger the death rate becomes. What about for birth rate? What's the trend here as population size increases? Someone else? What's our slope value going to be in this case? A. And what's the sign right before it? Negative. So what direction is the slope going to be on this line? Yeah. So we can move this birth rate over here, that'd be negative A n plus B naught. It's just flipped around. So what happens to birth rate as population size goes up? It decreases. That should make sense. If you're limiting resources, maybe you only acquire enough resources to have this many babies instead of that many babies. Fewer seeds rather than more seeds, something like that. So each of these are our per capita birth rate and our per capita death rate. For two parameters here, per capita birth and per capita death. Oops. Something wrong. So we can actually plug in the per capita birth rate and the per capita death rate in for R. Then we can substitute those two linear equations that we just talked about in for the per capita birth rate and the per capita death rate and expand it out, and we get this equation. And that's it. That's our new model that includes the effect of population size or density on both the birth rate and the death rate. And we can start to think about how that's going to affect the rate of population increase as the population size comes up. But this equation is a bit unwieldy, right? If our variable of interest here is population size, that now appears 3 times in the equation, right? So let's see if we can simplify it. Let's do it over here. I will leave. Purple. Oh, that's much better. Let's do purple. Okay, let me check what's on deck here. And then I will need some help. Yeah. So let's consider the behavior of this model, and let's see if we can find that parameter k somewhere in here, because this is already the exponential growth, the logistic growth model. But when I first showed you the logistic growth model, it had that parameter k in it. So let's see how we can relate these two to each other. We'll do that by solving for a special case. We'll solve for an equilibrium case where the rate of population increase is 0. Anyone think, just right off the bat, can you think of a population size, could be any size, where the population will not increase? 0. If all the individuals are dead, there's no one left to reproduce, the population is not going to increase. There's another solution to that. So we're going to try to find the other solution where we can solve for n, some population size, such that the rate of increase of the population is 0. Can anyone see what the first step would be if you wanted to solve for n here? Sorry,
When you divide by the, you get an answer.
for sure, you could absolutely start by dividing both sides by n. The equivalent of that would be multiplying both sides by 1 over n. So what happens to this side of the equation?
Still 0.
Still 0, right? Guess we don't need those anymore. Brackets. All right. Anybody else? What could you do next to get n by itself?
Just factor out n.
I would separate these first. I think you'd get there quicker if you did that.
Oh, like add 1 to the other side.
Yeah. Take this whole term here, this whole linear equation, and add it to that side. All right. So now a little more shuffling. Lots of pluses and minuses here, so we can get that. How can we get both ends together? I'm hearing people whisper it.
Add an to the left side and minus BO to the other side.
Good, yeah. Is that what you meant?
Yeah.
Looks good. All right, and now we're getting somewhere. What can we do? Now we can factor, right? Yeah. So what is n equal to?
BO minus BO over C.
Yeah. Or I think I wrote it in the book as a plus, or in the notes as a plus c equivalent. So there is a value of n where the population growth rate is 0, and it's determined by these two variables we've introduced, or these two parameters, I should say, we've introduced in combination with the birth rates and the death rates, assuming no competition, assuming there's no limiting resources. Can you remind me, what were these parameters specifying in the linear equations?
Strength plus density.
Yeah, the strength of density dependence on birth rate for one of them and death rate for the other. Death rate for C and the strength of density dependence for birth rate for A. So we just give this special case of n a name. We just give it something else to make us remember, okay, that's the special case of n when the population is positive, population size is positive, and the growth rate is 0. And we call that special case of n k, the carrying capacity. So this is where that k term comes from, it was in the initial equation. It's the population size, one way to define it is the population size or density that an area can support indefinitely. Or the number of individuals when the population, number of individuals in the population once births and deaths are equivalent and the population size is positive. When a population approaches that carrying capacity, that's why you get this S-shaped curve. It's getting closer, and then about halfway, it starts to approach, and so the growth rate starts to slow. So let's think about the Pinta Island tortoises again. You've thought about the tortoises in the context of population growth. Let's try to make a slightly more realistic model. Initially, we assumed no density dependence on their growth, and so we just had these birth rates that you calculated. But what if they were both affected by population size? What if both birth rates and death rates were affected by population size in an equal way, right? So the A value and the C value are going to be the same, not for any particular reason. I'm just trying to keep it simple. Well, then just as you all described to me earlier, you'd have this slope for the birth rate that's negative. Birth rate declines as population increases, and a death rate with a positive slope to that model, such that it increases as the population size increases. They're both measured as rates, so they can share an axis here. Can you plug in the A value, the C value, the B naught value, and the D naught value, and calculate carrying capacity? Take a shot at it in your notes. You've got the D naught, you've got B naught, you've got A, and you've got A and you've got C. What would K be given this equation that we just calculated? If you can do the addition and subtraction in your head, it should just be a division problem. Yeah.
Is that a negative? Did you put a negative?
Oh, no, you don't actually need to put a negative for, yeah, let me do that before here. You don't actually need to put the negative for the A here. That's up here, you think of it as kind of plus or negative 1 times A, if that helps you. So all you need is the actual A and C value. You don't need to use the signs associated with it.
And that n doesn't mean anything either?
Oh, right, so the n is also part of this equation, right? So
Yeah.
each of those that are on the board represents
Okay.
a part in the parentheses.
So 300.
If you work, if you haven't gotten it yet, but basically you've got you see it coming out there, 0.23 minus 0.03 and 0.000333 plus itself. And so then it's just a division problem. So if you have a given strength of density dependence on death rate and a strength of density dependence on birth rate, an A and a C value, and you know the birth rates under unlimited growth, you should be able to calculate K. Just to recap, thinking back to exponential growth, what would these lines look like if there was no effect of population size on birth rate and death rate? What would those lines look like if you could not predict the birth rate given the population size. See a few people thinking. If there was no relationship, these lines would both be what? Horizontal. Yeah, they'd be horizontal. So all you're doing is manipulating the slope by introducing this term here. So in this little intro example showing you these two graphs, I made A and C equal to each other. But they don't have to be in nature. You could have a different effect on birth rate or death rate. They might not even be linear in nature, but most different linear models for these exercises. So I borrowed these slides. How would K change? Oh wait. I forgot that I specifically removed the, so I specifically removed the numbers from this axis here, so that the question I asked you about calculating K wasn't given to you in the answer. What I should have then done is had the actual values on the axis here appear in the next slide, and it appears that I did not do that. The point where they intersect, the point where the birth rate and the death rate intersect, such that the death rate and the birth rate are equal. If you had birth rate and, such that birth rate and death rate are equal, that's when you would get a value here for n. And that n value is the special value that we call the carrying capacity. So birth rates and death rates are balanced out. So now that you know that this intersection point is telling you the K, telling you the value of K, how would K change if we increase the density dependence of birth rate on, increase the strength of density dependence on birth rate, such that this value becomes larger? This A value becomes larger.
K becomes smaller.
Yeah, it's going to shift that intersection point back here. Okay, so that becomes our new K value, just a little over 200, I believe, if you do the math on it. We're right at 200. Yeah, it's right at 200. What if you increase C? What if you increase the strength of density dependence on death rates?
K got bigger.
Did K get bigger?
It's still a little bit smaller.
It's still lower than
Yeah, it was
initially,
bigger than,
but bigger than the last slide, right? Because the difference here, the difference of change is less. So going up to 0.5 and 0.3 is less than going up to 0.6, 0.006. Yeah. So if you're like me and seeing things visually helps you understand the equations better, just think about how you can play with the values of A and C to change those slopes and move that intersection point one way or the other. And you can kind of imagine all sorts of scenarios, right? I left this in from a different version, but it gives you the chance to think about having really shallow effects on death, but strong effects on birth rate, really strong effects on death rate, and moderate effects on birth rate, and really moving that intersection point. So density-dependent population growth. A couple ways to think of it. It's the result of a decline in per capita birth rates and an increase in per capita death rates. That should be as the result of a decline in per capita birth rates and an increase in per capita death rates is the slowing of the population growth rate overall, is the slowing of DNDT as it approaches 0. But another way to think about it, I think is maybe a little easier to say out loud, is that density-dependent growth results from the negative feedback of a population on its own rate of increase. And that feedback is caused by, what we're going to talk about now, intra-specific competition. Competition for resources among individuals of the same species. So when we calculated K over here, we saw that the equation includes the strength and density dependence on birth rates and death rates. And those coefficients were our measures of competition. So we can think about K itself as a measure of competition. If K is really, really large for a given area, what would that tell you about the strength of competition, about the degree to which resources limit population growth, if K is really, really large? Yeah, if K is really, really large, there's lots of resources, and the population size is rather small, those individuals aren't going to experience the effects of competition very severely. If K is very small, then they're going to experience the effects of competition strongly. Very quickly, birth rates are going to go down, or very quickly, death rates are going to go up, or maybe both at the same time. So, another way to think about it, what effect would introducing supplemental resources to a community or to a population of organisms have on competition? You just add a bunch of resources, what would you be doing to carrying capacity? You'd be upping it. What happened at Academy Bay with the Finches? When it switched from bimodal to unimodal, what did they say when they talked about that transition?
Changing our resources.
They did talk about changing resources, adding supplemental resources to that area, but how did they describe the population of finches changing qualitatively? What happened to the variance in finch beak as it shifted to being unimodal? You switch from one mode to, or from two modes to one mode, but I heard another answer in the back.
The variance decrease?
In the paper they said it didn't decrease. The paper they said it stayed the same. Claire, do you want to add to that?
It kind of increased because they added that intermediate.
Yeah. The range of beak sizes remained,
Yeah.
and then they added to the population all of these intermediate beak sized finches that might have otherwise died because they weren't as good at accessing the really small seeds or accessing the really large seeds that were available naturally on the island. But they could survive when their food was supplemented. So the population of finches overall in that area probably increased. So, if you increase supplemental resources, what's that going to do to your A value, probably? Thinking about it in all possible terms, what's increasing the resources going to do to your A value?
It's gonna go up.
You're going to increase it. Yeah, good. And your D value and your C value?
It's gonna go down.
This C value, yeah.
So that's what I.
Okay, and we just talked about how that would affect K. It would increase K. So, let's think about this one. This is just another way you might see it presented at some point on a homework or a test or something like that. If you increase the access or availability of resources, what's that going to do to the strength of competition within the population?
Goes down.
If you increase, yeah. And so what's that going to do to carrying capacity?
Goes up.
Oh, right, that sense. And conversely, if you decrease the availability of resources, what's that going to do to your competition? Yeah. And your carrying capacity.
Yeah.
So you got to keep these straight in your head about which one affects which one in what direction. So here's our added term here that I introduced you at the very beginning that includes density dependence, or the strength density dependence, but it's in the context of K rather than in the context of the birth rate equation and the death rate equation. There's a couple ways that you'll see this written, and this K minus N over K, I think, is useful. Yeah, I borrowed this too. So, if you've got a small population size, if your N is quite small, approaching 0, what value will this whole term take? Or what value will that approach? If N is very, very small, it keeps getting smaller and smaller in your mind, what does this simplify to? Yeah, to 1, right? If N is 0, you just are left with K minus 0 is K, K over K. If that's going to be some real value based on the strength and density dependence on birth and death rates, it's just K over K, 300 over 300, we did with the tortoises. What does this become as N approaches the actual value of K, as N approaches carrying capacity? Yeah, 300 minus 300 over 300, that'd be 0. So if this is 1, this simplifies to 1, what equation does this remind you of? If you imagine substituting 1 in up there. Does it look like a model you've already seen? Yeah, okay, good. And what happens to the rate of increase as N approaches K? It goes to 0. That's that leveling off at the top of the curve, at the top of that sort of stretched out S curve, leveling off, because this rate of increase is getting slower and slower and slower as N approaches K. All right. So you all had some prep homework, and I think I've got some practice for you, but I think this might actually be a really good tool. I hadn't used it before coming here to Jewel, and I've used it a little bit each year since then. It's kind of old school, but it's nice and flexible in a way that most other tools that I've seen online for learning how these equations work are not. So this one has that advantage. I've got a link here at the end on how you can use it. But basically, you can open up a window and create a model of population growth, a logistic model. Logistic just means you're bounded on one side and the upper side, just like our fitness landscape was. But of course, this is population growth, not fitness. So you select a continuous logistic growth model. You select what kind of axes you want, what kind of plot you want. You want time and population size, or you want to see rate of growth in time, or whatever. So rate of growth and population size. In this case, you've got time and population size. And then you can plug in your parameters. The starting population size, in this case it's 5. You can set a K value, anything you want. I did 300 here, just like we did for the tortoises. And then an R value, 0.2. And you'll get this graph, you'll get this line, right? And you can see how it stretches and shrinks and changes as you play with those parameters, and see how quickly the population growth increases and then starts to slow. One of the things that's interesting about this one, I just kind of gave it away there, but how does the slope of the tangent to this line change as time increases? I heard someone say increases, and I heard someone say levels.
Increases then.
And then kind of level, yeah? And then what happens after that? How does the slope of this line change as you get towards carrying capacity? It gets shallower and shallower, right? So if you actually make that plot, which is very easy to do by just clicking dn dt versus n over here, you can see that as the population varies from 5 at the start to 300 at the carrying capacity, that's your rate of increase, dn dt. So what population size does the population grow the fastest under this model? When is the rate of increase highest?
140, 160.
Yeah, heard someone say 140, 160, I heard someone say 150. How would you describe this value, 150, mathematically? What is it related to? There's your 150 right here, maximum rate of increase. It's halfway to the carrying capacity. The population is growing fastest when the population size is 1/2 of K. Now, human population size has been increasing continuously. You guys might have heard that we're approaching 11 or 12 billion humans on Earth in the future. If you fit a simple model of logistic growth to human population size, it doesn't fit perfectly because there's more going on than just these parameters, but it fits pretty well. And the time when our population size was at 1/2 K was in the 1960s. That was when human population was growing the fastest ever. The population size is growing tremendously, but the rate at which it's growing is actually less than it was in the 60s. So we're somewhere over here in terms of human population growth. Of course, the amount of resources we have also is changing and increasing as we get better and better at agriculture. But it's interesting you can play with that model and see how it fits human population growth. Here's some examples of different parameters you can play with and adjust to try to understand it and think about how quickly a population reaches carrying capacity or how slowly, and which parameters affect that. And then you can, of course, look at how the rate of increase changes for each of those models, trying to find that 1/2 K value. So, what was I going to do? Oh, you can click and drag along these as well, and it'll give you little outputs, but this is what I was going to show you here. We just talked about that. Yeah, here's the link if you want to go download that software and play with it a little bit, practice thinking about relationships among these parameters. There's also an option on BIO Interactive from the Howard Hughes Medical Institute. It's a pretty nice one as well, although this one is just a little more flexible, even though this one's a little more recent. I'm going to post some homework for density-dependent population growth. We've got some papers to hand out to you. And for those of you who are in lab, the second in the later morning lab, I want to meet at normal lab time because I want to talk to you all about one thing, and then we'll break up into our subgroups.
Friday, homework. Friday. Giving you a heads up because it's going to take some work. In your groups, we're going to be talking about adaptive radiations. There's an assignment on Moodle about adaptive radiations. Each member of your group needs to find an adaptive radiation and prepare a short, like 5-minute presentation about your adaptive radiation. Obviously, Galapagos finches are not an adaptive radiation that you can use because we're talking about that like for 6 weeks now. But any other adaptive radiation in the world that you can think of, the criteria for what needs to be in that presentation are on the Moodle site. And as you land on a adaptive radiation to work on, inform your other members of your group, I've got this adaptive radiation, so that they know that they can't do that as well. So the idea would be that there will be 5 different adaptive radiations that are covered in each of your groups. You can have the same adaptive radiation in this group as somebody in the sports specimens. You can have the same adaptive radiation as they do, but no repeats in your group. So if you're not already connected with one another via text or email or whatever in your group, certainly do that so that you can communicate that adequately.
Well, if you have to remind yourself what adaptive radiation is, and you find 1 or 2, after you've put a few minutes into it, get creative. There's a lot of wild ones out there, not just the top 3 hits on Google. There's some really interesting ones. Plants, spiders, insects, other birds, mammals, they're all out there.
Ooh, happy face spiders.
Yeah.
Yeah. All right, luck. Dating. Paige. Jamie.
Yes, if you have that, I'll take the prep homework. If you submit it on Moodle, that's fine, or if you email me about it, it's okay. But I'll take these, yeah, prep homework. That's his.
David. Katie.
Yeah, prep homework if you have it. If you turn it in on Moodle, that's just fine. What's that?
Were these the only things that you think back?
Yes. Yes. I have the manual stuff we got on Wednesday.
It's a incredible work. It's 5 points. Feedback is right. Well, that's my evidence. I'll give it back to you.
Yeah. Prep homework,
He's got this.
I have it here. The manual homework, I'll have it back to you all on Wednesday. What are you looking at?
Yeah, you seem to understand what the paper is about, et cetera, et cetera. Yes, some writing issues, but doesn't everybody have writing issues?
Excuse me, darling.
Basically what we're talking about.
Do you have storage or the?
He has it. Oh, wait, no, sorry. I thought you had the whole stack.
Are we waiting for something?
Did you get some nice person?
I had it back.
Oh, then,
I can't tell from this whether you understand the paper. It appears that
still
you.
preparing the thing.
That's on mine.
Gosh,
That's the best I can come
for the bio lab.
up. Oh, yeah, that's fine. Yeah, that's excellent.
I also emailed it.
So they had it all
Yeah.
thing out to do.
Are you gonna need a communications person? Oh, yeah, okay.
I have a question.
Yeah.
I need to communicate with you.
Tomorrow, I
We were talking about,
volleyball at like 12.
are you free now, or do you have to go to class?
You have to be okay. Okay.
These look
So it'll be fine, as long as you don't have to meet.
I'll drop you an email since I know that you're coming person. We were talking about rubbing.
Run on to
What's that for?
Sunscreen and stuff like that. What we need to find is spray sunscreen, but not alcohol-based sunscreen.
Because that has a scent that will.
We'll have scent, and the alcohol may actually negatively affect the flowers.
Okay.
And spray, we can spray from the top and get it on there. We can also get spray from the bottom where there's short tops. So we can get it on the top. It's gonna be, yeah, so it'll be just a lot easier to work with than something that has to be applied with a swab or a
I'll
finger.
let my group know.
Yep. So, I was told this by a woman who uses sunscreen, and she's like, oh, you can get water-based sunscreens that are in spray bottles. I'm like, awesome.
Sounds great.
Yeah, so this is basically what we was talking about. So, as the population size gets bigger
Have a
and
great
bigger,
day.
Yep, you too.
you use up more and more of the carrying capacity that you have. So your carrying capacity is actually based on the number of individuals. So if your environment can only hold 500 individuals, and there's only 2 individuals there, you have a lot of carrying capacity left. So this thing here, which is a fraction of how much of the carrying capacity is currently being used, there's a lot of carrying capacity that's not being used. So the growth rate is pretty similar to the exponential growth rate. But if you can hold 500 individuals and there are 250 of you, well now half of that carrying capacity is being used up. So this whole thing is gonna fall to 0.5.
Would that mean K is equal to 1/2?
No, it means K is equal to 500, but you're at 250 individuals.
So what would that be then? Or would that not have any like variable?
So think about it like this. If you have, if the carrying capacity is 500,
My Dr. Jen.
you have one individual, 1 minus 1 over 500, that's pretty close to 1. Because what's 1 divided by 500? It's a really tiny fraction. If you have 1 minus 2 out of 500, that's also a little tiny fraction, so you're at close to 1. So your growth is basically R times N, multiplied times a really, something that's really close to 1. So you're basically growing exponentially. If you have 250
So,
individuals,
how did you said it's exponential?
yes, because this is exponential growth. This slows down exponential growth. Okay? So if, what's 1 divided by 500?
I have no idea.
Break out. Let's start it.
Zero, zero, two.
0.002. So this is 1 minus 0.002, so this is 0.998. So if R is 0.5 times 1 individual, then that increases by 0.5. But then you multiply that times 0.998. That doesn't reduce that very much. It's still pretty close to 5, right? If, on the other hand, 1 minus that fraction. 1 minus n over k. One minus 1 individual divided by carrying capacity is 0.002. So, sorry. This is 0.002. So 1 minus that is 0.998.
Oh,
Yeah. So if you have 250 individuals, this is now 1 minus 0.5, which is 0.5, which then, that's multiplied times whatever R times N is. So R times N is now 0.5 times 250, but then that whole thing gets multiplied times 0.5. So you're going to be growing half as fast as you would be if carrying capacity was not a thing. And when you get to 1 minus 499 over 500, this is 1 minus 0.998, which is 0.002. And so your growth would be 0.5 times 499, which should be growing pretty fast because you have a lot of individuals that are expressing that growth rate, but then you multiply that times how much carrying capacity you have left. And then that sends you down to how you mean growth. Okay, so think of this as the fraction of carrying capacity left after n individuals have used it up. So you have an environment out there with resources in it. If the environment will hold 500 individuals, but there's only 2 of you, there's a lot of resources out there.
so that means there's a lot of them.
There's a lot of room for growth. If the environment will hold 500 individuals and there are 498 individuals, then there's hardly any room for growth because all the resources are being used up. So think of this as a fraction of what's remaining.
So,
Does that make sense?
yeah.
So the exponential model of population growth includes this term, and the logistic model adds this term to it. That's the degree to which this is slowed down
Wait,
because
can
you're
you
using
say
up
that
carrying
again?
capacity. The exponential model of population growth includes this term, that term there. So that's exponential growth. That's growth where population grows and grows and grows and grows and grows because nothing is limiting it. The thing that limits population growth is this part that is additional to the equation. So this is exponential growth, this is logistic growth. The exponential model of population growth included the R n term, and the logistic model adds the term 1 minus n over k. How is the rate of population growth related to the population size? Well, as population size gets bigger and bigger and bigger, it slows down your growth because this part gets multiplied times that part. So that's what it's doing. which is just the same thing as saying k minus n over k. Well, if we split this out, it's k over k minus n over k. K over k is 1, n over k is k. These two things are exactly the same. This is basically saying, this is your carrying capacity. From that carrying capacity, 250 individuals are using it up. Of the 500 that you have, this then is that same fraction. This is the fraction of carrying capacity remaining after this number of individuals have used it.
So it can never go past any capacity?
No, in theory. No, it will approach carrying capacity and level off. Because it creeps up to it. We'll go to 0.5 to 0.4 to 0.3 to 0.2 to 0.1 to 0.05 to 0.04 to 0.03 to 0.02 to 0.01 to 0. I'll just creep right up to it. Because the population responds instantaneously to these changes.
Okay.
Can
Okay.
we ask maybe you move your lesson
Oh yeah, sorry. Is this all the people in your class?
for today apparently?
Oh, I'm sorry. I was expecting your class to actually arrive. But it has.
I'm hoping for a few more. One, I know will be absent.
My apologies.